Have you ever noticed how a dashboard bobblehead bounces in its own predictable rhythm, regardless of how chaotic the road gets outside? That motion isn't random. It follows specific rules of physics, and we can decode them using the foundations of mechanics taught by Dr. Chandan Chattoraj. To understand vibration, engineers strip away complex shapes, visualizing objects as a simple block connected to a horizontal spring. To track it, we lay down a yardstick to measure its position over time. Then, an initial nudge pulls the block, starting the movement. By translating a physical object into these basic parts, a mass, a spring, and a starting push, we can use math to predict how any structure will behave. If our block slides on a perfectly smooth surface with no friction or air resistance to slow it down, it will bounce back and forth forever. This is what we call undamped free vibration. To map this endless bouncing, we use a 4-step checklist called the equilibrium method. Step 1 is choosing our measuring scale, like the horizontal yardstick we just set up. Step 2 is finding the block's natural resting place. Before we flick it, it spends its time sitting still right in the middle. We mark this center line as our 0 point. Step 3 is all about isolation. We freeze time mid-slide and identify the forces pulling on the block, which in this model is just the spring trying to snap it back toward that center line. Step 4, we apply Newton's second law. We state that the mass of our block, multiplied by its acceleration, is exactly equal to the force the spring is exerting. This gives us our complete equation of motion. It proves that the block's acceleration is constantly changing, depending on how far the spring is stretched from its resting point. By rearranging that equation, we can find the system's natural frequency. This tells us the specific speed at which our block inherently wants to bounce. Look at the letter K, which represents the spring's stiffness. If we swap in a stiffer spring, it pulls back harder and forces the bounces to happen much faster. The letter M stands for mass. If we replace our original mass with a heavier block, it becomes harder to move. The extra bulk slows the system down into a long, sluggish rhythm. You can observe this on a guitar. A thick, heavy string vibrates slowly to produce a deep note, while a thin, tight string snaps back and forth to create a high note. By isolating mass and stiffness, engineers can calculate the unique structural voice of almost any object. But what happens if the system isn't just left alone after one nudge? What if a continuous outside force keeps pushing the block over and over again? When an outside push connects with an object's natural frequency, like a parent timing their pushes on a swing, those forces combine to create a much more complex vibration response. And how does the math change if we hang our spring and mass vertically, introducing gravity? This diagram shows that gravity stretches the spring down, creating a new resting point. But once it settles there, the math dictating the bounce itself remains exactly the same as our horizontal model. Whether it's a bobblehead on a dash or a skyscraper in the wind, the relationship between mass and stiffness is the universal rule that allows us to master vibration analysis.